For the next several minutes, I'll guide you through the inception of the Biostasis program, the structure and style of the experimental science we envisioned as we designed its application, and what DARPA needs to see from you as you formulate your approaches and proposals. So on slide 10, yes, that's me. Slide 11. This is a breakdown of the team that was responsible for the inception of the program and will be responsible for its management and technical review moving forward. Now, myself as the program manager, Miss Elizabeth Kilpatrick, who handles financial oversight, communications, and administration of the program, and Dr. Gina Kost, who provides technical support as well as serving as a primary point of contact for the teams who are actually performing the scientific effort. Contracting support is provided by Dr. Stephanie McElhaney at the Army Research Office, where she serves as the contracting officer's representative. Now, to be clear about roles going forward, as the DARPA PM, I am the principal arbiter of the scientific content and value of the program, but Dr. McElhaney represents the office that has direct oversight of the execution and maintenance of the contracts that are awarded. In other words, I judge and manage the scientific merit and progress of the program. She monitors and judges the degree to which the science is actually satisfying the contracts. Now, the email address for all questions regarding the Biostasis program is listed below, as well as on the broad agency announcement that was issued last Friday. Now, moving on to slide 12, I'm going to go over the program in a similar trajectory as on the BAA, so it's recommended that you have a copy in front of you, either old school style on paper where you can make brilliant notes in the margins that will be illegible later, or on a fancy second monitor or a tablet so you can follow along and refer to specific passages should the need arise. There is an email address listed in blue that will allow you to directly ask questions. Now, we'll do our best to answer your questions in as timely a fashion as possible, and ultimately all of them will be answered and posted via the FAQ section. So on slide 13, this is the overarching issue we are attempting to address with the biostasis problem. The fact that on the battlefield, time is never on our side. Now, this applies to both literal battlefields where people are wounded, sometimes critically, and need rapid medical intervention, as well as more metaphorical battlefields as encountered by civilian healthcare practitioners, and even those battlefields pertaining to hostile environments that threaten biological therapeutics and reagents with spoilage or loss of potency over time. Now, the fact is that we as a nation have distributed operations around the world, often in regions and areas with minimal access to basic healthcare infrastructure. And one of the most limiting resources under these conditions and generalizable to critical care intervention writ large is time. The operating principle of the biostasis program is that time can mean different things in the context of biology, considering that all life is essentially a set of massively parallel and interdependent biochemical reaction networks. Chemical reactions all have rates. In effect, if we slow reaction rates, we slow life. And if we slow life under certain stressful circumstances, we may be able to prolong the functional integrity of the system to enable better therapeutic intervention. Slowing life to save life is the goal of this program. Now on slide 14, why do we as the Department of Defense care so much about biological time? Well, the fact is that many current state-of-the-art strategies to provide critical care and to bolster the logistical burdens of therapeutic compounds are insufficient and prone to failure under certain conditions. In fact, it has been reported that as many as a quarter of the combat deaths over a 10-year span in Iraq and Afghanistan were the result of potentially survivable injuries, as in would not have been fatal had they occurred in closer proximity to appropriate medical infrastructure. Now, the unfortunate truth is that even with all the modern accoutrement of advanced healthcare, some injuries are simply too extreme. For example, in the panel on the far left, you can see what's called the trimodal distribution of death following a potentially life-threatening injury. In the first few minutes, about 50% of individuals that are injured will die due to acute massive blood loss, penetrating injury, or head trauma. An additional 30% will die over the following minutes to hours, generally due to progressive airway obstruction or uncorrected blood loss. And another 20% will expire over the following days to weeks, with sepsis and complications from permanent tissue damage the most frequent culprits. Now, the principal tools available to medical practitioners today for first-line critical care are largely identical to what has been available for decades, such as first aid, blood transfusions, rapid medical transport to more comprehensive care facilities. In fact, in the article that first described this distribution, the suggested remedy for the first mode of death was avoidance. In other words, don't get hurt, you'll be fine. So clearly there's exploration space for us to do better. Now, the most outcome-determining factor in critical trauma care, as well as acute infection, is the interval between when injury occurred or symptoms appeared and when supportive and restorative treatment begins. Now, this is the so-called golden hour. Now, it's golden because the time there is precious, and hour is actually a misnomer, and most of the time the operators have much less than an hour. Acute trauma care is not the only application space where a biological pause button is handy. The transport and storage of biological reagents and therapeutics can be a logistical nightmare in terms of the cost and required infrastructure to maintain a cold chain. And the closer we can get to a system or set of chemical adjuvants that enable room temperature or anhydrous storage of these critical therapeutics would be a revolution in and of itself. And finally, as I mentioned previously, acute infection can take root and progress much more rapidly than the identification of the causative agent and its effective treatment. Severe sepsis following injury or infection can run rampant and change the scenario from a survivable condition to a fatal one very, very quickly. And it bears repeating here that a common thematic element is that more time to act is a huge boon to the practice of modern medicine, regardless of its practical scenarios. Again, we are trying to slow life to save life. Slide 15. To wit, the Biostasis program goal, as succinctly stated here, is to develop novel molecular interventions that will reversibly pause biological processes and protect the functional integrity of that paused biological system. Now, my background in science is as a molecular pharmacologist, and as such, I envision generating a whole new class of chemical interventions that can be used to extend the window of time for treatment following injury or infection. And not by traditional means or subtle tweaks to existing methods, but by going after the molecular nature of biochemical reactions themselves and shifting the states of cells and tissues to reduce the rate at which they function, which should also then reduce the rate at which their dysfunctions accumulate to cause death or permanent damage. Therefore, the major goals of the program are to develop a new capability to reversibly slow the processes of biological systems in a manner that is scalable, from simple cells to complex systems that can also be used under a variety of conditions and help us get away from the costly and unwieldy reliance on cold chain to produce and store certain biological therapeutics and reagents. Now, we on the Biostasis team have thought about how it could be done, and we will discuss those topics and hypotheses shortly, but ultimately, there is no lab at DARPA. We are not the world's great experts on these topics. You are, and it's up to you to figure out how to get it done. Now, on slide 16, there are a set of 3 potential approaches to tackling the challenge of biostasis. In a sense, they all come from a first principles conceptualization of the molecular nature of cryptobiosis. Now, I'm not a specialist in cryptobiosis or in the molecular biology of cryptobiotic organisms, but I am a fan of their resilience. And being a bit of an outsider in the field affords me a comfortable, naive distance from which I can look at all the things that are common across the well-studied organisms and relate them to the biochemical principles that govern all life, whether cryptobiotic or normobiotic in nature. Now, broadly interpreted, what we're operating under is the notion that if we look at all the excellent work over the past several decades that has explored the molecular mechanisms underlying the fantastic abilities of these highly resilient organisms, we can see that at the core, there is the need to reversibly arrest and protect the structural and functional integrity of cells. Now, while the precise nature of that capability differs according to specific organisms, it shares a common capacity in that protein motion is effectively restricted, and that the transition of water from liquid to ice, or present to absent, doesn't completely denature the proteins due to the sudden change or loss of hydration shell. The obsession that I have with proteins isn't just because they're the necessary catalysts and components of almost every chemical reaction taking place in biological systems, although that is a critical aspect of the science here. Now, it has more to do with how we fundamentally manipulate protein shapes to change functional states and signaling processes in cellular systems. A protein's function is dependent on its ability to dynamically alter shapes, such as following the binding of a ligand or the formation of a complex. And protein structure-function relationship studies are legion, but what is also important to recognize here is how much function relies on flexibility and disorder, how much dynamic control of protein function can be obtained by manipulating conformational stability. In other words, if protein disorder contributes a significant functional attribute, is the reverse also true? And how do we get there in a controlled and predictable fashion? Now, the states possible in a complex organism are vast. Many different temperature zones and fluctuations, dynamics and hydration, solute concentration, as well as solute composition, means that the actual 3D shape of proteins in any cell at any given time probably occupy many potential conformations and are freely distributed across that distribution. Now, that protein folding funnel is depicted on the top left and encapsulates a concept we thought about for how to effectively and reversibly slow protein functional dynamics. Pharmacological chaperoning is a known phenomenon and may actually underlie some of the therapeutically relevant effects of a number of drugs. Now, by binding to proteins and changing their overall potential energy, thus reducing conformational flexibility and reducing energetic burden during their folding, chaperoning, transport, etc., stressful states in cells can be ameliorated. Cells already employ protein chaperones and adapter proteins for precisely these regions, to control cellular energetics by reducing interaction space and functional capacity of proteins during times of metabolic stress or structural compromise. Now, what if we searched for a set of promiscuous pharmacological chaperones? Most protein chaperones have a relatively restricted number of specific clients within cells and are often specialized according to cell type. Most pharmacological chaperones, likewise, have specific targets by virtue of their target specificity and also, therefore, have rather restricted effects. But if we found a class of molecules that could effectively enter cells, reduce conformational flexibility of all proteins, and thereby their per unit catalytic function, according to a common interaction mechanism, but be subject to some degree of kinetic regulation such that the resulting protein-ligand interaction wasn't irreversible, and the drug like chaperone could eventually be metabolized and deactivated, would that suffice to promote some form of functional stasis that can be leveraged to protect overall functional capacity while temporarily restricting a cell's activity? Now, a related concept is intracellular crowding. A well-known cryptobiotic mechanism is to pack the cell with an appropriate solute, like a sugar such as trehalose, which serves to both restrict protein conformational flexibility, like a box filled with packing peanuts, while at the same time creating the conditions where state transition of water can result in vitrification. In fact, modeling studies have shown that specific protein conformation restriction via selective chaperoning mirrors the change in flexibility, and by proxy its activity, due to crowding. A concept we thought could be particularly interesting, given recent advances in biocompatible materials and intracellular hydrogel formation, would be to explore whether certain polymers could be assembled on demand inside cells to impart some degree of structural rigidity and reorientation of water in order to mimic the conditions of cells that have selectively imported stabilizing crowding factors. Now, finally, we have the king of all cryptobionts, the tardigrade, the indestructible organism, sort of, under certain conditions. Last year, a mechanism was reported for tardigrade environmental tolerance that involved the stress-initiated synthesis of a set of intrinsically disordered proteins, termed TDPs, for tardigrade disordered proteins, that are at least partially responsible for the astounding recoverability of that organism. Now, these TDPs could be transferred to other simple eukaryotic and prokaryotic cells as ectopically expressed genes and confer some degree of dehydration tolerance. The molecular mechanisms of these TDPs are still being elucidated, but it is suggested that they serve multiple synergistic functions by packing within cells and promoting vitrification under freezing and dehydration, and by acting as chaperones to other proteins due to conformational flexibility and proximity-induced changes in binding affinity. Can we use these proteins with their sequences already elucidated to serve as lead compounds for the iterative synthesis and evaluation of TDP mimetics that can penetrate cells passively or be taken up via active transport to behave as they do in tardigrades but in human cells? Now, this is a critical point. These three concepts are by no means the only avenues open to exploration in order to achieve the goals of the Biostasis program. They merely represent some potential approaches to the problem that seem practically tractable. We are open to hearing about and reviewing other approaches that can address the problem and provide the right type of solution. As a matter of fact, I'm absolutely thrilled to see what everybody comes up with in order to tackle this unbelievably difficult problem. Now is probably as good a time as any to describe what we specifically do not want to see in a proposal. First of all, anything related to organ banking or ex vivo organ harvesting and preservation, any surgical interventions that require medical device utilization and/or medical infrastructure to achieve rapid fluid exchange or decreases in temperature, anything evolving or related to cryogenic preservation. The whole point of this program is to explore new chemical biology approaches to control cellular function by interacting with and controlling protein conformational flexibility and metabolic state. We already know cold works. We already know how cold works. We already know what cryoprotectants there are. All that research is great. This is not the place for it. Genetic manipulation. Now, I specifically do not want to see approaches that that require the rewriting or transfection of novel genes in order to produce the effects. It's not of any use to us if we have to reprogram all the cells in an organ in order to make it resilient. Now, on slide 17, the BAA breaks the program down into two major technical tasks. Task 1 is to design, build, and test biostasis interventions. Task 2 is to evaluate their performance in progressively more complex biological systems and establish metrics for safety, efficacy, and generalizability. Any proposal you craft must address both of these tasks. The duration of the program is set at 5 years. There will be a base period of 18 months during which you're expected to produce proof of concept data and build the pipeline required to rapidly screen and describe activity parameters for your chosen approach. Milestones specific to each phase must be met on time in order to justify transition into subsequent phases and receive funding beyond the base period. On slide 18, the program was essentially envisioned using the model of drug discovery and preclinical evaluation, where early on you have a set of lead compounds, or at least a unifying hypothesis on which to iterate and test for in vitro and in vivo efficacy. It is expected that these test compounds or approaches will be formulated in a way such that they can be passively administered to a biological test bed, and those methods will translate to use in organisms and/or cells and biologics with therapeutic value. And finally, we want to see evidence for the molecular mechanisms and functional consequences of the stasis induction you propose. Just like in drug development and screening, mechanism matters, and we want to see how things work as they're being pursued and optimized for use. Now, as described in the BAA, critical aspects here are the use of first principles derived from cryptobiotic mechanisms as a starting point for the iterative optimization in a design-build test cycle. We want to see proposers with a strong background in the field from which they're proposing to leverage as an approach to biostasis. I may have some great ideas on how to build a race car, but I guarantee McLaren isn't going to take a proposal from me very seriously. And moreover, we want to see proposals from laboratories with access to all of the research infrastructure required to meet the program goals. As much as I would love to give new performers a shot at seeing their dreams come true, now is not the time to build a brand new lab and learn how to use a bunch of new experiments. Not a bunch of new instruments, rather, and do new experiments. We understand that the experimental burden of this program is large, so you may be able to purchase use-specific equipment to aid your process, but it should be equipment you're already familiar or proficient with. Proposals must also specifically list 5 or more functionally distinct bioassays that are going to be used to measure the biostasis effects. These can be anything from purified enzyme complexes, simple globular proteins, reconstituted ion channels, and artificial lipid bilayers. The choice is yours. We just need to see experimental evidence that the approach produces a reliable, generalizable, and mechanistically tractable effect that can be used for its designed purpose. It is also up to you to decide on your own intermediate milestones and experimental validations of the approaches you are pursuing. Now on slide 19, this is all about task 2. Task 2 is related in that it represents the functional evaluation and feasibility of utilizing your novel biostasis approaches in a relevant context. And we anticipated what we referred to as a relatively flat total effort, with percentages in each task that change as the program proceeds. Now, early on, the chemical space for biostasis intervention discovery is large and requires a lot of focus and iteration in order to produce things that actually work. They should be tested in relatively high throughput fashion in very simple model systems to get indicators of effect magnitude, mechanism, and generalizability. And as the program proceeds, we expect the number of compounds to be evaluated to decrease, while optimization of a small set will proceed and increase, and the complexity of the model system in which they're evaluated will also increase. Reversibility is also a major goal in Task 2. Biostasis without reversibility is essentially just fixation, and that's not what we want. Okay? In phase 1, simple cell models or protein complexes are sufficient to serve as a proxy for a complex biological system. By phase 2, it is expected the in vivo models will involve some form of tissue culture or heterogeneous organotypic system. And by the transition into phases 3 and 4, we'll be looking for evidence of safety and or efficacy using animal models to actually establish metrics for pharmacodynamics and pharmacokinetics. On slide 20, this phase chart shows the primary metrics and potential application spaces for successful transitions between phases. Early on, we expect new interventions to perform at least as well as standard lab practices for cryopreservation of cell lines or the storage of enzymes and other functional biomolecules. The chassis system can be as simple as necessary to facilitate rapid evaluation of effect. But in phase 2, we expect multicellular models with complex metabolic outputs to be employed in order to increase the mechanistic insight and the demonstration of the effect. The viability requirement increases here as well. For phase 3, the major shift is in the survival percentage. Now, while 90% may be an A in most classes, imagine suddenly losing 10% of the cells in your hand. That would be catastrophic. So we want to see something that can preserve at least 98% of cell viability after intervention. And by phase 4, we're looking towards safety evaluation and pharmacodynamics, pharmacokinetics in animal models. Now, this table is a great tool for you to use as you craft your projected research plan and the proposed performance metrics. Now, on slide 21, here's a little more detail. We need to see that the methods you employ do not introduce significant and potentially long-term damage to the genome. We also need to see that the induction of a stasis-like state does not take longer than a typical controlled rate cooling for cell cultures preserved in DMSO. And in phase 2, we want to start seeing mechanistic data at least at the level of cellular activities. Now, these can be anything like genetically encoded sensors for kinase activity, cell signaling pathways, motility, etc. Something with quantifiable output and biological relevance to the system that's being studied. And by phase 3, we want to see all of the above, plus some agnostic profiling data that can be used to assemble a systems-level mechanism for the effect and help guide future efforts and optimization. We also want to see the complexity of the model systems increasing to the point where we can address questions of generalizability. If the intervention is working as advertised, it should work in multiple types of cells, or all cells in a complex tissue. And by the final stage, quantitative outputs for physiological effects and detailed context-specific pharmacodynamics analysis will determine whether or not the approach is sufficiently performing to transition into actual preclinical evaluation for therapeutic development. That is the goal. On slide 22, here are some quotes directly from the BAA that you need to take to heart as you consider your proposal. Before each phase transition, you should plan on a demonstration of capability that addresses the milestones for that phase. It can use the model system of your choice, but it should be conducted and presented as a single large-scale experiment that contains all of the pertinent information for the application of your biostasis approach, such as the degree and duration of stasis achieved, the methods used to measure that effect, and the proposed mechanisms and evidence for those mechanisms by which stasis is induced and then reversed. We will work with you to design the appropriate challenges to the system by which stasis efficacy will be judged, but should be consistent with end-user applications. Okay? It's not going to be very useful to our performers in the field if we develop a new technology that works really, really well in the laboratory but doesn't actually do anything against any of the things that they encounter. Now, it's not a requirement that you prepare and perform an end-of-phase demo at a specific time and location, rather that the demonstration serve as a test of your capabilities by the end of that phase so that progress can be effectively determined. Now, working with DARPA can be an enlightening experience. We're your partners in research and can help you achieve great things as long as we agree to follow certain rules and make certain that we have an understanding from the start. Now, I understand as a fellow scientist that discovery and innovation is not something that can be dictated. And that said, experimentation with no application in mind is not how progress towards a goal is achieved with any alacrity.